I will talk now about logistic regression, which is a method that we find in both statistics and machine learning. Logistic regression is actually not a regression method, it's a classification method. So I thought it's worth giving you the idea of logistic regression and how it works for classification. So we dispose again of training data with feature values and labels. The labels can be binary labels, -1, +1, or 0, 1. We want to learn a classification function, and the classification model here is said to be linear if it is represented by a linear function, that is a linear hyperplane. So far we have seen several examples of classification: classifying spam from ham emails, classifying tumors from benign or malignant, and also let's take the example in this lecture about credit default or not default. So we have customers in a bank, and we want to be able to decide for a new customer whether he will be defaulting or not. So the data is two features, balance and income, and the label is the default, yes or no. So if we plot this data, it's not a perfect data. There is some overlap between the classes. So we have on the x-axis the balance, on the y-axis the income, and we have positive and negative examples that say whether the customer has defaulted or not. In fact, we can't really predict credit card default with any certainty. Suppose we want to predict how likely is a customer to default. This is an output of probability between 0 and 1 rather than a binary classification 0 or 1. So it makes sense and would actually be more suitable and practical for the bank to know how likely is the customer to default with the value between 0 and 1. So in this case, we are talking about an output that is real. So we are talking about a value between 0 and 1, but that is bounded by 0 and 1, which makes it as a classification problem. What we are trying to model in this case, a function that maps the input to the output, and what we're trying to model specifically is actually the probability of default given the data description. So probability of default is equal to yes, given that the balance value is such and such. You might be wondering whether we should just use linear regression. After all, we have a set of feature values, and we have an output that is 0 or 1, and linear regression allows us to find a numerical value as a prediction. Yes, however, first of all, this will work only for binary classification when we have two classes, and won't work for multi-class classification when we have three or more classes. Also, if we use linear regression, we could expect that the prediction will be outside of the domain 0 and 1, so we have to make sure that this has to be really tightened into 0, 1. And finally, the model can actually be poor. Here's an example. So in the credit card default example, we're going to put all the positive examples on the 0, probability of 0 default, and all the points that have a probability of, this is our input data. Our input data is a feature values with the label that is either 0 or 1, or -1 and +1. It's not a numerical value as label, right? So we have our data points that are laying actually on the 0 and the 1. If we do linear regression, we're going to get this line that actually has a very poor performance in predicting whether the probability that the customer will default or not. Just like for linear regression, we're going to model the problem with a linear function. So we're going to write y as a function of x, function of the input or the feature values, as beta 0 plus beta 1x. This is the equation of a line. One more time, just like for linear regression. So in the specific case of the example, we're going to write the default value of the label as beta 0 plus beta 1 times the feature balance, right? Okay. So we aim to find the function f that actually is bounded between 0 and 1, and the function f is the probability of the y, the default value is equal to 1, given that the data we have x. Okay, so we use in this case the sigmoid function that actually is g of z, is either e to the z divided by 1 plus ez, or also it could be written as 1 divided by 1 plus e minus z. Okay. So this actually is a beautiful S function that actually is bounded between 0 and 1, right? That actually goes to 1 whenever z goes to infinity, and goes to 0 whenever z goes to minus infinity. So this is a function that actually smashed the data between 0 and 1 and has a nice S shape that would actually give us a good distribution of the probability of y given x. So now we have a new f of x. A new f of x is a sigmoid function, the g function, of linear combinations of our features, beta 0 plus beta 1x. In general, f of x is the sigmoid function of the sum of beta j xj if we have d dimensions. In other words, we're going to cast the output to bring the linear function quantity between 0 and 1. One can use any other, by the way, any other kind of S-shaped function as a G to cast the results into between 0 and 1. So here's a comparison between what an S function would look like on the data of credit default as compared to the line that we are obtaining actually on the using linear regression. So note again that logistic regression is not a regression method but a classification method. So here's an example of using logistic regression to make a prediction. So suppose we have learned the betas, and the betas are beta 0 is minus 10.65, beta 1 is 0.0055. What is the probability of default for a customer with $1,000 balance, right? So I'm going to plug these numbers into the function that the logistic function, the probability of default in this case equal yes. Given that the balance is $1,000, we're going to plug the numbers that we have for the betas and for the $1,000 into the logistic function. We have 1 divided by 1 plus e minus z, which will make beta 0 plus beta 1 x1, right? So which will bring us to a probability of default given equal yes, given the balance of $1,000 of 0.00576, which means that the customer is unlikely to default. Okay, if you want to predict a class, we can make a threshold. Whenever the logistic function g of z is bigger than 0.5, we predict the class to be 1. Otherwise, we predict the class to be 0. But if you want a probability prediction, then we could use just simply the logistic function without the threshold. So now how can we find the betas? We're going to do something similar to find the betas as we did for linear regression. So recall we calculate some loss function that is the difference between the predicted and the actual label, right? So we're going to define the loss as half of the difference between the squared difference between the predicted and the true label, okay? So we're going to put that into the risk function that actually is the sum over all the data points of the loss function. All right, so remember that f of x is now the logistic function. It's not the linear function, which means that f of x minus y squared is no longer the quadratic function we had when f was linear in the case of linear regression. So now the cost is a little bit more complicated to calculate because it's a nonlinear function. So which means that if it's not a linear, if it's not a quadratic function, then we will have many local optima. Hence, the gradient descent-like methods will not find the best global optimum. So we need to find a different function that is rather convex. Convex means that there is, if we descend the gradient, we are going to find only one local optimum. All right? So we're going to transform this function here. The logistic function is interesting because it has this S-shaped function. It can get us a probability between 0 and 1, but it's not convex. So I'm going to convexify it. So here's a new convex function. If the cost of f of xy is either equal to minus log f of x if y is equal to 1, or to minus log 1 minus f of x if y is equal to 0. So we could observe these two configurations, these two cases that are actually also drawn in these pictures. If y is equal to 1, if the projection f of x is equal to 1, means that we didn't make a mistake, the cost is 0. If y is equal to 1 and the prediction is f of x is equal to 0, then the cost is infinity. So which means that this function here makes sense. It has a nice features for predicting whenever y is equal to 1. If y is equal to 0 and we don't make a mistake, the cost is infinity. If y is equal to 0 and we make a mistake, the cost is 0, right? So we're going to define a function that's actually combining these two functions here. And the function is actually, because we have y is equal either to 0 or 1, we can write the loss f of xy as minus y log of f of x minus 1 minus y log of 1 minus f of x. So you could see that in the function. If for y equal to 0, we are going to have this term, we go to 0. We have minus 1 minus 0 log of 1 minus f of x, which is minus log of 1 minus f of x, which would correspond to this case here. And if we have y is equal to 1, then minus y log f of x will be minus log f of x, and these terms will be going to 0. So we're going to have only minus y log f of x if y is equal to 1, just like this case. Okay? So the risk function in this case would be minus 1 divided by m, sum of this different loss of f of x, y, which will bring us to this function here. All right? So we're going to do something similar afterwards with gradient descent, just like we did for linear regression. I'm not going to go into the details here and leaving these details to your machine learning class that is coming after the AI class. Thanks very much for your attention.